Okay guys, in this video we're going to talk about another aspect of molecular geometries. We're going to talk about the dipole moment of a molecule. What the dipole moment it's a measure of the degree and direction of charge separation within a molecule. So this is called the polarity. As you know, molecules contain protons and electrons that are arranged in space, and if the center of positive charge, which comes from the nuclei of the atoms, is at the same location as the center of negative charge, which is due to the electrons, then we say that the molecule has no dipole moment. However, if the center of positive charge and the center of negative charge are at different positions within the molecule, then we would say that the molecule has a dipole moment. It is a polar molecule. One of the origins of one of the ways of thinking about where polarization comes from, it comes from electronegativity differences between atoms. So, for example, we've talked about how when you have a diatom, the electrons that make up the covalent bond between the two atoms are not evenly shared. Okay? Some atoms are more electronegative than other atoms, and they draw the electrons towards them to a greater extent than the more electropositive atom. So, for example, in a carbon-hydrogen bond, carbon is slightly more electronegative than hydrogen, and so there's a polarity to this bond. There's a slight positive charge on the hydrogen, represented by this little plus, and then the carbon takes on a slight negative charge. And so that arrow points to the carbon. So the dipole moment in a carbon-hydrogen diatom points from the hydrogen to the carbon. Think of it as a little arrow in space, a vector. In boron fluoride, fluorine is much more electronegative than boron, and so the fluorine atom is going to draw electrons towards itself, leaving the boron slightly charged, slightly positively charged, and then the fluorine is going to be slightly negatively charged. Not quite a full unit of charge, mind you, just we think of these as partial charges. So there's going to be a dipole moment in boron fluoride that points from boron to fluorine towards the more electronegative center of the molecule. In carbon dioxide, each of the bonds are polar, right? Oxygen has a much larger electronegativity than carbon, and so there's a little bond dipole that points from carbon to oxygen. But there's also one that points from this carbon to that oxygen. Notice that the two arrows oppose one another. It's a bit like a tug of war. In the end, because the molecule is symmetric, these two bond dipoles cancel out, and there is no net dipole moment for the molecule. So we would call CO2 a nonpolar molecule. The situation is different in water, which has two very polar bonds. Oxygen is very electronegative, hydrogen is electropositive, and so there's a bond dipole moment that points from the hydrogen to the oxygen for both of them. In this case, the two arrows don't cancel out. In fact, they reinforce one another in this vertical direction. And so there's an overall or net dipole moment in water that points from this region of the hydrogen atoms, and it points up towards the oxygen atoms. Water is considered to be a very polar molecule. And so what we're being asked to do here is to evaluate the geometry for these two molecules, given that they both have a non-zero dipole moment. That means that they do have dipole moments. So SO2 has a dipole moment. Let's consider this using some paper. So just without going through the full VSEPR model evaluation, let's just look at the two different geometries. Okay, so a linear geometry would place the oxygens on either side of the sulfur. A bent geometry would be more something like this, where you've got that arrangement. Now, oxygen is a very electronegative atom, and so sulfur-oxygen bonds are going to have a bond dipole that points from the sulfur to the oxygens. Right? Sulfur is going to be more electropositive than oxygen. In the linear arrangement, however, the two bond dipoles are going to cancel out, and so this would be nonpolar. Whereas in this case, when you add these two bond dipoles together, they're going to reinforce each other in that direction. Okay, and so there's going to be a net dipole moment. So this one is going to have, it's going to be a polar molecule. And so since the problem tells us that SO2 has a non-zero dipole moment, that means the molecule is not nonpolar, it's in fact polar. And so the bent structure is the correct one. This is the one we want to choose. For part B, again, we are to take phosphorus trihydride as having a non-zero dipole moment, which means it has a dipole moment. And we're being asked to evaluate the trigonal planar structure versus the trigonal pyramidal structure. Well, in a trigonal planar structure, you'd have a perfect triangle. Okay? I think that phosphorus and hydrogen have about the same electronegativity, so there's not going to be much of a bond dipole moment. Anyway, let's just say that the phosphorus is a little bit more electronegative than the hydrogens, and so we'll put those going this way. Okay, so that's what the hypothetical trigonal planar structure would predict. Again, all of these arrows, they are going to cancel each other out. Okay, and so for this arrangement, we would expect there to be no dipole moment, not a non-zero dipole moment. However, for the trigonal pyramidal structure, phosphorus, hydrogen, where the molecule has a three-dimensional shape, here there would be a net dipole moment coming up like that. So this would be nonpolar, and this one would be polar. And so this is the one that you would choose given the setup for the problem. Okay, it's going to be the trigonal pyramidal structure. Here we have another one of these types of problems. Okay, we're looking at bromine trifluoride. Okay, we're told that it does have a dipole moment, so it has a non-zero dipole moment. Which of the following geometries would be consistent with that? Trigonal planar, right? That would be something like this. Okay, we would not expect a dipole moment there. Okay, so it's not going to be that one. That one's not possible. Trigonal pyramidal. That would look something like this. Okay, yeah, that one would have a dipole moment, so that's possible. T-shaped. That one would have a dipole moment as well. So it could be this one or it could be that one. Both of these geometries are consistent with the information given. You'd need to go through the full Lewis structure to figure out which geometry it should be. And I'll leave that as an exercise for you guys to try. Here we have which of the following would be expected to have a dipole moment of 0 on the basis of symmetry. So here we need to actually go through the Lewis structure and figure out the geometry and try to find out which structure would be, which one would be polar, which one would be nonpolar. For the sulfur for this sulfur compound, sulfur is going to be in the middle. You're going to have oxygen like this, and then you're going to find the chlorines out like that. Okay, probably a double bond here. This one is going to have a dipole moment, so this is going to be a polar species. I didn't completely do the Lewis structure, but I've sketched out most of it. So this is going to be a polar structure. For the silicon tetrafluoride, here's the Lewis structure, save for the lone pairs on the fluorines. It's going to be a perfect tetrahedron. This one is going to be nonpolar. And then for the OF2, you're going to wind up with a Lewis structure that looks like that about the oxygen. Much like water, the fluorines would also have lone pairs on them. This is going to be a bent structure. It's going to be polar. So for the problem, which one would have a dipole moment of 0? The nonpolar one. So this is the correct answer for this problem. Well, I'm going to go ahead and stop this video here. And the next one will start, I guess, chapter 8, I believe.